Hi everyone, my name is Gongguang from 360 Up Lab. I'm glad to have this opportunity to share this topic with you. As we know, because of the existence of many mitigations in Android, nowadays it's very difficult to remotely root Android devices. But today, I'll show you how I remotely root the toughest Android device, the Pixel phone. At the beginning of this talk, I want to introduce our team shortly. I'm the team leader of 360 Alpha Lab. Our main research fields are Android system security and Chrome browser security. We have found more than 300 vulnerabilities in Android system. We won the highest reward in the history of ASR program in 2017. Because of the exploit chain introduced in this talk, we have won the highest reward in the history of all Google VIP programs in 2019. We have also had different targets in different phone contests. A brief look at today's agenda. I'll first explain why Google Pixel phone is a tough target from two aspects: the price paid by vulnerability blocks and the results of mobile phone-to-on in last 3 years. Next, I'll introduce remote attack surface of Android devices. Then, I'll share my experience of pawning Android device 6 times in different competitions. Next, we'll overview the exploit chain named TiYunZong. It can remotely root a wide range of Qualcomm-based Android devices, including Pixel devices. After that, I'll detail the 3 vulnerabilities in the chain and how I chain these 3 vulnerabilities for exploitation without any RP. At the end of this presentation, I'll demonstrate how to get a reverse shell with root permission of a Pixel phone by accessing a malicious link in Android. Which is the most secure smartphone? It's an open question, and I think there is no standard answer. Android and iOS are the 2 most popular mobile operating systems in the world, and there are too many arguments about which one is more secure. There are different answers from different perspectives. If we answer the questions from the perspective of the price paid by vulnerability blocks, it seems like Android is more secure than iOS. Zerodium pays up to $0.5 million for Android FCP zero-click exploit chain, which is higher than iOS FCP zero-click exploit chain. If we assume Android is more secure than iOS, the remaining question is, which is the most secure phones among Android phones? It's easier to answer than the previous one. Google Pixel phone often have more up-to-date OS versions, security patches, and vulnerability mitigations than other Android phones, which makes it more difficult to be attacked. As shown in table, the Pixel phone is the only device that was not pawned in mobile phone-to-on competitions in last 3 years. While iPhone was pawned 7 times in total. Other Android devices include Samsung Galaxy, Huawei Mate, P series, Xiaomi Mi devices were pawned several times in the contest too. Many exploits demonstrated in the contest target Android devices existed in outstated OS component or unsecured customized code. So we can conclude Pixel device is a tough target. Before I talk about my exploit chain, I want to give you a attack surface analysis of remotely compromising smartphones. As shown in the picture, remote attacks of smartphones can be divided into two categories by attack vector: attack through internet and attacks through adjacent network. Normally speaking, attacks that exploit vulnerabilities in browsers, apps, and emails can be launched through internet more easily. Attacks that exploit vulnerabilities in NFC, Bluetooth, Wi-Fi, and baseband are mostly launched through adjacent network. Attacks from internet is more destructive than attacks from adjacent network, but the former often needs some interactions, such as clicking a URL, opening an email, or instant message. It's relatively easier to launch an attack from adjacent network without interaction than from internet. Broadband and Bluebond are amazing adjacent network attacks. It's hard to say which attack is more harmful between zero-click adjacent network attack and one-click internet deployable attack. The exploit chain I used to remotely use the Pixel phone is a one-click internet deployable attack chain. This table summarizes some remote working exploit chains found by me target Android in recent years. In Mobile Contour 2015, I found Nexus 6 with a single vulnerability. I first get RCE in Chrome render process, then I turned this RCE into a UXSS vulnerability, so any JavaScript could be injected to Google Play website, and any app could be installed from it. In .0 Rama 2016, I found 3 Android phone with a single exploit chain. The exploit chain also started from a VS bug, combined with a Chrome IPC weakness. The web view in Android had no sandbox at that time. By exploiting the VS bug again in a web view, Chrome sandbox could be bypassed easily. This sandbox escaping method doesn't work anymore because web view is sandboxed now. Is also sandboxed now. In PwnFest 2016, I found a Pixel XL with a single vulnerability once more. The method is similar to .on 2015. After PwnFest 2016, Google updated the remote apps installation features to prompt the user to enter their password, which makes this form of attack difficult, but it took more than a year for them to mitigate this kind of attack. As of Chrome 77, such isolation has been enabled on Android devices. It's nearly impossible to leverage the RCE to UXSS method. In Mobile Contour 2017, I found a Galaxy S8 with 2 bugs, an OOB access bug in Samsung Internet Browser and a use of unmapped vulnerability in Samsung Exynos GR-Lock module. I can get a reverse shell with system user permission through this exploit chain. In 2018, I found a Pixel phone with 2 bugs. A V8 engine bug is used to get RCE in sandboxed render process. A bug in Android, the libgr-alloc module is used to escape from Chrome's sandbox. Together, this exploit chain can be used to inject arbitrary code into system server by accessing a malicious URL in Chrome. In 2019, I found episode 3 with 3 bugs. I named this exploit chain TiYunZong. So, what is TiYunZong? TiYunZong is from a very famous Chinese kung fu story, and these kung fu allow people to move upward swiftly and effortlessly as if clouds are the stairs. The exploit chain includes 3 bugs, which are just like the cloud stairs of TiYunZong. The exploit chain is composed of 3 bugs, 2 Chrome bugs and 1 Qualcomm KGSL driver bug. The attack vector is malicious links. Once victim accesses a web link controlled by attacks, the attacker can get reverse shell with root permission of the attacked phone. This figure shows how to remotely get root permission with the exploit chain. First, an OOB access bug in V8 is exploited to achieve remote code execution in a Chrome render process. Render process runs in the SE Linux domain isolated app and is highly sandboxed. For example, it can't access the GPU driver directly. CVE 2019-10567 is a bug in Qualcomm GPU driver, but it can't be triggered directly from isolated app domain. In order to trigger this bug, we need to escape from isolated app domain with the help of CVE 2019-5870. Firstly, it is a use after free vulnerability in the media component. A compromised render process can trigger this vulnerability through module code. By exploiting this bug, arbitrary code can be executed in Chrome privileged process. This process runs in the SE Linux domain untrusted app. It can access GPU driver. I'm going to detail how to exploit these 3 bugs separately. First, let me introduce the Rce vulnerability. This bug exists in the talk code of Chrome V8 JavaScript engine. V8, the code stub assembler, provides low-level primitive as a thin abstraction over assembly. V8 Tokyo is a V8 specific domain-specific language that is translated to code assembly, code stub assembly. In V8, many JavaScript built-in functions and objects are implemented by V8 Talk. This figure shows the build process of Talk code. If there is any bug in Talk code, it will be propagated to the generated CSS code and then to the generated snapshot file in the end. The snapshot file is embedded into Chrome to speed up the initialization of all built-in functionality in V8's heap. Before we talk about the Rce bug, we have to know the JS function memory layout first. JS function in Chrome V8 is the internal representation of function in JavaScript. The size of these objects in V8 is not fixed. It may contain the field prototype or initial map or not. The field prototype or initial map is the last field of JS function if it has. This is the field information of the function array. has prototype slots means the array function has the field prototype or initial map, so its size is 64 bytes. This is the field information of the function parseInt. It has no prototype slot, so its size is 56 bytes. In most situations, if a function is a constructor, it has a prototype slot. If a function is not a constructor, it has no prototype slot, but there is an exception. The function proxy is a constructor, but it has no prototype slot. So the bug is here. The token macro get-derived map didn't check whether the argument new target contains prototype or initial map, and access it directly, so it's an out-of-bound access. It's easy to trigger the bug. You can only need one line of JavaScript code. As shown on screen, you can create an untapped array with reflect.construct to trigger the bug. Reflect.construct will call the token function create tapped array. This function will call the variable macro get-derived map. Because the new target argument is set to the proxy function, so the OOB access will be triggered. But if the above JavaScript is run in Chrome simply, nothing special will happen, although the OOB access has already occurred. It is because that after loading prototype or initial map, the value will be treated as a map. Its constructor is loaded and compared with target. And in most situations, this value is a legal map, but its constructor is not the same as the target. So execution flow will bear out to slow pass. Everything is normal. If the value isn't a map, execution flow will bear out to slow pass 2, while it fails to be casted to a map. Because the slow pass will make all the access useless. To exploit this bug, the execution flow must return a map in fast path. So here is the exploit strategy of this bug. First, we have to free the object below the proxy function. Then we occupy the free space with an object whose map's construct is uint8array. We name this map x, and then drop all reference to map x, so the garbage collect will mark the map x as garbage and will sweep it in scheduled sweep task. Then we trigger the OOBX bug before map x gets swept by GC, so the variable get-derived map won't bear out to the slow pass. The pointer of map x will still be used in create tapped array. After sweep task finished, we occupy the free space of map x with a map whose construct is uint32array. So we can get a map from tapped array. Its map is uint32array, but its layout, especially its element kind, is uint8array type. It's easy to implement arbitrary read and write with this malformed object. With the ability of arbitrary read and write, we can enable module.js binding and exploit the following module vulnerability to escape from Chrome sandbox. Next, I'm going to introduce the ELP bug. Chrome uses a multi-process architecture. it isolates render process from other privileged process. As the picture shows, the main process that runs the UI and manages tabs is called the browser process. The GPU process is a process used when Chrome is displaying GPU-accelerated content. Likewise, the tab-specific processes are called render processes. Normally, render process has the lowest privilege. The GPU process and the browser process have high privileges. Render processes are highly sandboxed and many interactions between them and the system are processed by other privileged processes. In Android, render process runs in the domain isolated app. The GPU process and the browser process run in the domain untrusted app. The Rce bug occurred in a render process, while the EOP bug occurred in the GPU process. The communication between processes is via IPC. There are two IPC systems in Chrome, legacy IPC and the module IPC. Module is Chrome's new IPC system. The EOP bug can be triggered by module call from render process. It's a URF vulnerability in Chrome's media component. It is related with the interface of content decryption module. This module allows Chrome to play DRM-protected HTML5 video and audio. The IDL format of the content decryption module is shown on the screen. The function in line 3 is responsible for initializing the CDM. If initialization succeeds, CDM ID will be non-zero and will later be used to locate the CDM at the remote side. The initialize function is implemented in C++. If initialization succeeds, the function on CDM created will be called. This function will be called. The cause of the vulnerability is that there is no restriction to the number of the calls of the function initialized. If this function is called twice through module call, in debug version, this dechecker will be triggered, and all CDM created would be called twice too, which without the same module CDM service would be registered twice in the function or CDM created. In the function register CDM, two CDM IDs would be mapped to the same module CDM service in line 4. When module CDM service was destructed, only one CDM ID was unregistered and removed from the map CDM services. The other CDM ID was mapped to a diagonal point. After that, if the function get CDM context ref was called with a formation the CDM ID, the URF would occur in line 6. Module CDM service can be configured to be run in different processes. It can be configured to run in the browser process, the GPU process. It also can be configured to run in utility process. Desktop Chrome is desktop Chrome configure CDM service run in utility process. Utility process is highly sandboxed, just as render process, so it can't be exploited to escape sandbox in desktop Chrome. But luckily, module CDM service is configured to be run in the GPU process by default in Android. So we can exploit this bug to access the GPU drive directly. The UF object is a module CDM service. Its size is small. It has only 48 bytes. There is a lot of noise in the heap in this size range. So it's hard to reoccupy the freed module CDM service object with controlled data. Luckily, a member pointer points to a large object. Its type is a medial DRM bridge. The size is 168 bytes in debug version and 160 bytes in release version. We can occupy the memory of the freed medial DRM bridge. Use the control data. So we can control its virtual table, overwrite its virtual table. It seems like we can use RP to finish the exploit, but there is another problem. We can't allocate memories with known address in GPU process. So we don't know where the virtual table pointer can be modified to point to. We need another information disclosure bug to fetch a virtual table with known address. Then we can finish the exploit by rope. However, it's not a good choice. There is a simpler solution. As we know, random process and the GPU process have the same memory layout in Android. They are forked from the same process, so we know the base address of most shared library in GPU process. The shared library leave LLVM GLnext use the system function. So there will be a system function point in this shared library after it's loaded. Now, if we modify virtual table point to point to near system function point, when UF occurs, the system function is called. The argument is controllable too. We can use this simple method. We can use a simpler method, return to libc to execute any shell command in GPU process. So we escape from the Chrome sandbox. Next, I'm going to introduce the root vulnerability. The Google Pixel phone has an original GPU. It uses KGSL driver developed by Qualcomm. The picture shows the architecture of KGSL driver. Apps can create Adreno contexts with different priorities. Normally, there are 4 context priorities: 0, 1, 2, and 3. 0 denotes the highest priority, and 3 denotes the lowest priority. Each Adreno context is bound to a ring buffer, depending on its priority. Because Adreno contexts have 4 priority, there are 4 ring buffers relatively. There are RB0, RB2, RB3, and RB4. Similar as CPU has different privilege levels, GPU can run in different modes. Adreno GPU can run in two modes, privileged mode and unprivileged mode. Some pages and registers can only be accessed or modified in privileged mode. After an app creates an Adreno context, the app can send the GPU command to the context by our control. Each context has a command queue. The received GPU command are queued. The dispatcher is the core module in KGSL. It runs in a separate kernel thread. The Google Pixel phone has an Adreno GPU. It uses the KGSL driver developed by Qualcomm. The picture shows the architecture of KGSL driver. Apps can create Adreno contexts with different priorities. The Google Pixel phone has an Adreno GPU. It uses the KGSL driver developed by Qualcomm. The picture shows the architecture of the KGSL driver. Apps can create Adreno contexts with different priorities. Normally, there are 4 context priorities: 0, 1, 2, and 3. 0 denotes the highest priority, and 3 denotes the lowest priority. Each Adreno context is bounded to a ring buffer, depending on its priority. Because Adreno contexts have 4 priorities, there are 4 ring buffers relatively: RB0, RB1, RB2, and RB3. Similar as CPU has different privileged level, GPU can run in different modes. Adreno GPU can run in 2 modes, privileged mode and unprivileged mode. Some pages and registers can only be accessed and modified in privileged mode. After a map creates an Adreno context, the app can send the GPU command to the context by out control. Each context has a command queue. The received GPU command are queued. The dispatch is the core module in KGSL. It runs in a separate kernel thread and keeps reading commands from the queue and submitting them to ring buffers. After commands are submitted to a ring buffer, the write point of the ring buffer is updated. After the GPU executes some commands, the read point is updated by GPU. Every context uses different page tables, but some pages are mapped globally to all contexts. This list shows all globally mapped pages in Pixel phone. Note that Scratch in Lab 5 is a globally mapped page, and we will exploit it later. Some pages in this list are not only mapped by GPU, but also can be modified by CPU. Scratch is one of these kind of page. The Scratch memory is one page data that is mapped into the GPU. This allows for some shared data between GPU and the CPU. For example, it will be used by the GPU to write updated read point for each ring buffer. The format of the Scratch is shown in this table. The first 16 bytes are the read point of 4 ring buffers. As aforementioned, the read point of ring buffers are stored in Scratch memory. The Scratch memory is mapped in GPU space and CPU space. Read point are sensitive data for KGSL driver. The driver reads read points when allocate buffer from ring buffers, but the scratch memory is wrongly set to writable by normal GPU command processor instructions in this function. In this line, the function KTSL allocate globe allocate a global memory without read-only and privileged flag. So RPTRs can be modified by GPU command processor instructions in unprivileged mode. In the function adrenal ring buffer allocate space, the variable RPTR in line 5 is read from the scratch memory. As RPTR can be modified to any value, the function can be conjugated to return a wrong ring buffer point. As a result, we can overwrite the exist command processor instructions and inject initial command processor instructions into ring buffer to execute. So how to exploit this bug? There are few public documents about the internal architecture of Adreno GPU. We can only speculate some internal behaviors of the Adreno GPU. RPTRs in the scratch memory are updated by the GPU, but it seems that they are just shadows of the real read point used by the GPU to fetch instructions. Modifying the RPTR in the scratch memory doesn't affect the execution flow of the GPU. Luckily, it affects the kernel allocation space from ring buffers. RPTR points to the next instruction, which will be executed by the GPU, and WPTU write point, and the write point points to the start of free space of a ring buffer. There are two scenarios of the position of read PTR and write PTR. Read PTR less than or equal write PTR, or read PTR larger than write PTR. When read point is less than or equal to write point, if there is enough space from write point to the end of the ring buffer, allocating is simple. We just need to advance write point and return the original write point. If there isn't enough space towards the end of the ring buffer, we have to look for space from the beginning of the ring buffer up to the read point. If there is enough space, advance write point from the beginning of the ring buffer. Otherwise, the allocation will fail. When read point is larger than write point, if there is enough space from write point to read point, we just need to advance write point and return the original write point. Otherwise, the allocation will fail. Read point in scratch buffer can be set to any value by normal GPU instruction because of the bug, so we can follow the allocation function. As shown on screen, assume that after GPU executing some instructions, RPTR is less than WPTR. A request of allocating a large space from ring buffer is issued. Because of the space at the beginning and the end is small, the request will fail. If we modify RPTR in Scratch memory, for example, it once is near WPTR. Then some space will wrongly marked as free. At this moment, if another request of allocating another space from ring buffer is issued, it will succeed. But some existing command processor instructions will be overwritten. The adrenal GPU will execute instructions still from the original RPTR, resulting in executing unaligned instructions. It means executing from the middle of an instruction. Treat some data of the instruction as opcode. So it's possible to inject arbitrary command process instructions into ring buffer if we can write arbitrary data to ring buffer. When GPU instructions are dispatched to ring buffer, CP indirect buffer prefetcher instructions are inserted into ring buffer by KGS driver. GPU instructions provided in user mode are in indirect buffers. They are not copied into ring buffer directly. The execution flow will jump to indirect buffer when CP indirect buffer prefetcher instruction is executed. It's difficult to write arbitrary code into ring buffer. Luckily, we found another bug in user profiling command. User profiling command is used to read the GPU tickets at the start and the end of GPU command. The GPU address of the profiling buffer is controllable by user mode and can be set to any value. GPU address is 8 bytes. It's enough to write a CP lock or CP set protected mode instruction into it. As shown in the picture, it's CP instruction sequence of executing our control KGS GPU command. CP indirect buffer prefetcher instructions are wrapped by other instructions, such as instructions to enable and disable protected mode, instructions to start and end user profiling. If protected mode is disabled, GPU runs in privileged mode. Many privileged registers can be modified. Protected module can only be disabled by CP instructions which runs in ring buffer. CP instructions executed in indirect buffer have no permission to disable protected mode. As mentioned before, we can execute a CP instruction from its middle, so we can exploit the bug as shown in the picture. Before we trigger the bug, the layout of a ring buffer is shown on the left. The first CP indirect buffer prefetcher will jump to indirect buffer. In this buffer, there is a CP wait reg main instruction, which will wait until the value in a specific GPU address to become a specific value. At this moment, assume the condition is not satisfied. So, the reader pointer will point to the next CP induced buffer prefetcher instruction. Then we trigger the bug in the highest priority context, so we can preempt the wait instruction to modify reader pointer near WPTR, which deceives the GPU kernel driver into think the space before reader pointer is all free. Then we execute our control KGSL GPU command 2 times to override the ring buffer, as shown in the middle. The GPU address of the second and the fourth user profiling command are carefully designed as a CP NOP instruction and a CP protected mode instruction. If the wait condition is satisfied at this moment, after executing some prefetched instructions, CP NOP instruction will be executed as shown on right. CP NOP instruction will NOP all the instructions until the CP sets protected mode. The CP set protected mode instruction will disable protected mode, so the following CP induced buffer prefetch instruction will jump to induced buffer with protected off. Now we can change TTBR to any value by instructions in induced buffer. Is a powerful primitive we can exploit to read and write arbitrary physical memory, including code segments in kernel. It's easy to exploit it to get arbitrary kernel code execution. At the end of my presentation, let me show you a demo of the whole exploit chain. First, we launch a web server in the attack's computer. Then, the victim phone accesses the malicious link. We can see a reverse shell will be established. Please wait for a moment. Okay, we get a reverse shell. Then the attacker can execute the downloaded binary file to exploit the root vulnerability to get a root shell. We run the root exploit. You can see we have root permission. And the SE Linux is disabled. I show the conclusion. In this presentation, I first explained why Google Pixel phone is one of the most secure smartphones. Then I introduced the remote attack surface of Android phone and 6 Android exploit chain found by me over 13 years. After that, we overviewed the exploit chain which can remotely root the modern Android devices, including Google Pixel phones. At last, detailed 3 vulnerabilities in the chain and how I exploited them. Okay, that's all for my talk. Thanks for your listening. Any questions?
Okay. Hello. Okay, thank you everyone for your listening for my talk. If you have any questions, you can contact me online, and I will be very happy to answer that.